We're back, and we're continuing on looking at Lewis dot structures. Now, in some molecules, we can see different ways to draw the Lewis dot structure without changing the arrangement of the atoms. All we do is change the bonds and the lone pairs. So let's look at an example where there's multiple ways to draw the Lewis dot structure and talk about which one is the right way when all of the ways obey the Lewis octet rule. Okay? So we're going to look at chm1-. All right, guys. Now, cn1-, it's a polyatomic ion. We've got one oxygen, one carbon, one nitrogen. So that's 6 electrons and 4 electrons and 5 electrons. So that's 15 electrons. I add one more electron because it was negatively one charged. That's 16 electrons. Okay, carbon's going to go in the middle, oxygen and nitrogen on either side. I connect up with single bonds, that's 4. That leaves me 12 electrons. 2, 4, 6, 8, 10, 12. I now have 0 electrons left. So I'm going to have to make double bonds or triple bonds to fix it. Okay? So let's look at options. One option is the following. A double bond with the oxygen, a double bond with the nitrogen. Okay? Another option would be to triple bond with the nitrogen and just keep a single bond with the oxygen. A third option would be to somehow abuse the oxygen and get it to triple bond. Okay, so I've got 3 options. Everything's seeing 8 valence electrons. Now, looking at this one, we'd probably be a little bit suspect of this one because oxygen doesn't really like to triple bond. Nitrogen triple bonds without too much problem. Both of them can double bond. So I get a feeling right from the beginning that this one probably isn't going to be the best Lewis dot structure that we can create because of that fact that it's got the oxygen triple bonding. But we want a way to judge which one of these Lewis dot structures is better. Okay? Now to help us judge which Lewis dot structure is better when we can have more than one way to draw it, we're going to use something called formal charge. Okay? And what we see here when we have 3 possible ways to draw it, these are called resonance structures. A resonance structure is one of the possible ways to draw a Lewis dot structure without changing the order of the atoms, just arranging the bonds and lone pairs differently. The real molecule is probably going to be a blending of the structures called a resonance hybrid, okay, or a resonance structure. Kind of like taking, your book talks about taking a red mule and a blue donkey, a red horse and a blue donkey and making a purple mule. That's kind of what we're doing here. Okay, it's not going to look perfectly like any one of these, but it's going to show some of the characteristics of maybe all of them. Okay, the resonance structure, all these resonance structures that I've drawn here, these Lewis dot structures, are not the real bonding depiction of the molecule. And the bonds don't flip from one arrangement to the other. Turns out that atoms do this to us all the time. We know better than you. And in situations like this, where we have double bonds and triple bonds, it can actually sometimes smear a bond across the whole molecule. So that when we're talking about molecular orbital theory, I'll bring up again smearing bonds. Okay? But we can smear, or we can't, nature does. We just have to obey what nature tells us. Now, in the hybrid, the resonance hybrid, electrons in that second bond or third bond can be delocalized, the smearing. Okay? And of different resonance structures, the possible ways to draw the Lewis dot structure, there's usually one that is better and will most closely resemble the molecule that we end up with. To help us figure out which one is the better choice, we're going to use formal charge. Okay, so let's talk about formal charge and then we're going to do formal charge. Okay, formal charge is a false charge, and what we're doing is we're calculating what the charge of an atom would be if all of the electrons were evenly shared in every bond. Okay? And we ignore electronegativity effects. So formal charge is equal to the number of valence electrons an atom started out with minus the number of unshared electrons we see in its valence in the Lewis dot structure plus 1/2 of the electrons that it shares. The sum of the formal charges always have to add up to the actual charge on the particle. Okay? So let's calculate the formal charge for oxygen, carbon, and nitrogen in OCN1-. So let's come back over here. All right. Formal charge for oxygen. Well, oxygen has 6 valence electrons to begin with, okay? And it sees 2 in a lone pair, and it's seeing 6 in a bond. So 1/2 of 6 is 3, 2 plus 3 is 5, 6 minus 5 gives me a formal charge of 1. The formal charge for carbon here is 4 minus 0 plus 1/2 of 8. 1/2 of 8 is 4. 4 minus 4 is 0. The formal charge for nitrogen, nitrogen starts out unbonded with 5 valence electrons. It sees 6 in lone pairs. It's seeing 2 in a bond. So 6 plus 1 is 7. 5 minus 7 is a formal charge of -2. Okay? Don't worry, we're going to talk about what they mean in a minute. Formal charge for oxygen here is going to be 6 minus 4 plus 1/2 of 4. That's a formal charge of 0. Formal charge for carbon is going to be 4 minus 0 plus 1/2 of 8, 0. Formal charge for nitrogen is going to be 5 minus 4 plus 1/2 of 4. So that's a formal charge of -1. Okay? For our last option, the formal charge for oxygen is 6 minus 6 plus 1/2 of 2. Formal charge of -1. Formal charge for carbon is going to be 4 minus 0 plus 1/2 of 8. Formal charge of 0. Formal charge for nitrogen is going to be 5 minus 2 plus 1/2 of 6. Formal charge of 0. Okay? Now, when we're looking at formal charges, number 1, we want the numbers to be as small as possible. 0 is the gold standard here. So the more 0 formal charges you have, the better. So if I look at these 3 options, these 2 have 2 formal charges of 0. This one has 1 formal charge of 0. These 2 are definitely better resonance structures than this one. Strike number 1 against this one. Okay? Next thing is we want the more electronegative element to have the more negative formal charge. Between oxygen, carbon, and nitrogen, oxygen is the more electronegative. It's the second most electronegative element on the periodic table with an electronegativity of 3.5. Nitrogen's electronegativity is 3 and carbon's is 2.1. Okay? So if I'm going to have a negative formal charge, it's better to have that negative formal charge on oxygen. So this one is our worst. Okay? Between these two, this is our best. Because I've got 0, 0, -1, and my -1 is on oxygen. This one also has 0, 0, -1, but it has the -1 on nitrogen. So of these three possible resonance structures, this one is our best. And the molecule is most likely to look like this one. May have a little bit of the character of this one, probably almost nothing of the character of this. Okay? Now, for our test, I'm going to give you resonance structures. And I'm going to ask you which one is the best. So you're going to have to calculate the formal charge, and you're going to have to label them best to worst. Okay? So that's something I expect you to be able to do. I am not going to give you this and ask you to draw the structures and then make the determination, because if you don't get the structures right, you can't do this part. So I will give you this and this, and I'm going to ask you to do this. Okay? So formal charge. All right. And I keep dropping things. Okay, guys. Keep going on down. All right, now, let's see, organic molecules. Let me look at this practice problem and see if I want us to look at some of these organic molecules. It's 5.7 on 217. Okay. I will get there. Okay, guys. Now, we've been looking at just molecules that have a single central atom. But organic molecules, molecules that involve carbon and hydrogen, and they can contain nitrogen, oxygen, sulfur, but they have to have both carbon and hydrogen to be considered an organic molecule. They can have long strings of central atoms with things hanging off of them. We talk about them having a backbone, okay? A central backbone with things hanging off of them. So they have a skeletal structure. So if we look here, we have CH3NH2. Here is its skeletal structure. Let's see if we can do the Lewis dot structure for this guy, starting from its skeletal structure. Okay? So let's look at it. So we're given CH3NO2, and we're given this skeletal structure. Okay? Now, we know we have one carbon at 4 electrons. We have 3 hydrogens at 1 electron apiece. We've got 1 nitrogen, 5 electrons, and we've got 2 oxygens at 6 electrons apiece. So 2 times 6 is 12, plus 5, that's 17, plus 3, that's 20, plus 4, that's 24 electrons. Okay, let's connect up. 2, 4, 6, 8, 10, 12. That leaves us with 12 electrons. 2, 4, 6, 8, 10, 12. Okay? So that's all 12 electrons. Now, if I look at it, carbon sees 2, 4, 6, 8, it's fine. The hydrogens all see 2. The oxygen sees 2, 4, 6, 8. Oxygen sees 2, 4, 6, 8. Everything's good there. Nitrogen only sees 2, 4, 6. So I have to fix it by making a double bond. And there's two possible ways we could do it. We could take a lone pair off of here and fold it in, or here and fold it in. It doesn't matter. They're going to be equivalent resonance structures. So I'm going to fold that in and make a double bond. And I get a molecule that looks like that. Now, if I gave you the skeletal structure, I would expect you to be able to draw in the bonds and the lone pairs. Okay? I am not going to give you something like this and expect you to be able to create the skeletal structure. You'll get that skill later when you're taking organic chemistry. But I do want you to notice the CH3 here. Notice CH3 here, the NO2, the NO2. The way this formula is written tells us something about how the molecule was put together. Okay, it tells us something about the structure. So that's example problem 5.7. Okay, now your book also is part of 5.7. Is just a little bit me. Get this all the way up here. Oh, did I? Oh. Let's get this to focus. Okay, focus. Auto. Okay. All right, guys. Now, here's something that I won't do to you, but you might see it in mastering. It says, draw the Lewis structure, including resonance structures for diazomethane, CH2N2. Okay? For each resonance structure, assign formal charges to all the atoms that have formal charge. I don't like this one very much. We're not going to do it because I would never do that to anything like that to you on an exam. I'm going to be a lot better than that. Okay? So, just wanted to point that out to you. Watch out for things like that. But again, the way that it's written tells you something about its structure. Okay? So watch out. All right. Let's move on to our next topic. Okay? Now, we're going to talk about bond energies and bond length. Bond energy is the energy required to break 1 mole of a bond for a compound in the gas phase. Bond energies are always going to be positive values because the process of breaking a bond is always endothermic. Okay? When you make bonds, making bonds is exothermic, releases energy, but breaking bonds is endothermic. So if we think about glucose, okay? It's not the breaking the glucose up that gives us the energy. It's actually when the carbons and the hydrogens and the oxygens in glucose form water and CO2 that we get energy out. Glucose has weak bonds. Water and carbon dioxide have much stronger bonds, okay? So, and don't worry about the fact that it talks about a mole. Just think about the mole as the chemist does it. Okay, go ahead and screw it. So here are some bonds, and they're bond energies. One of the things I want you to notice here is that a double bond is always stronger than a single bond, and a triple bond is stronger than a double bond. But notice that a triple bond is not 3 times as strong as a single bond. that's a hint that the second bond between two atoms and the third bond between two atoms are different than the first bond between two atoms. Okay, here look at a single bond in oxygen and a double bond in oxygen. A single bond in nitrogen, double bond in nitrogen, triple bond in nitrogen. Okay, and notice just different bonds, different bond strengths. Okay, let's scroll up. Bond length represents the average length of a bond between two particular atoms in a large number of compounds. Different compounds, you can see the bond between the exact same two atoms be slightly different lengths. So when we talk about bond lengths, we're talking about an average length. In general, the stronger the bond, the shorter the bond is going to be. So strong bonds are shorter, okay, than weaker bonds. So the table that goes along with table 5.3, you could look at them side by side. No, we're not going to here, but you can go back and look, and you can see that if you looked at the carbon, notice that carbon-carbon single, carbon-carbon double, carbon-carbon triple, they get shorter. If we go from carbon single to carbon double to carbon triple, they get stronger. Okay? So, we are now in a place to go to 3D, so this is a good place for us to stop. Hello?